All right, guys. So let's solve this problem, but let's solve it with synthetic division. So do you guys remember where I find my multiplier? It's quite easy to find, right? Because it's literally what you are evaluating your polynomial at. So notice this is telling you to find p of -3. So that's telling you that you need to evaluate with the value of -3. So that is what is my multiplier. Now, you do need the leading coefficient of each and every single degree of your polynomial. Now, remember, if you are missing a degree, what value do you put? A 0. So keep in mind that this first term here has a degree of 2. This second term has a degree of 2. This term has a degree of 1. Now notice that we always have to have our degrees through 0. So keep in mind that when I get to that point of the leading coefficient of 0, I'm going to have a place value there. So let me go ahead and do this. What's my leading coefficient of the first one? -1. How about the second one? A +1. The third one, a -1. And how about my last term there? If you're missing a term or the degree of a term, what value do we put again? 0, right? And then now you just have to remember to do the synthetic division, the algorithm part of it, just the repeated steps. The first thing you're going to do is bring down your first leading coefficient, which in this situation is a -1. Remember, when it's below the line, you're going to multiply it by your multiplier. So -3 times a -1 is a +3. 1 plus 3 is a +4. That's the way I always like to memorize it. Multiply below the line, add above the line. And then you just repeat the process over and over. -3 times 4 is a -12. And then a -1 plus a -12 is a -13. Finally, multiplying -3 times -13, I believe that's a +39. Add those up, you end up with a +39. Always remember that given the remainder theorem, if you use synthetic division, your remainder is the value it comes out to. So p of -3, so your input, when you input into your p function, is going to be 39. You'll notice that if you were to plug in -3 in for all the x's and do the math correctly, you would end up with the 39 as well. Now, on the test tomorrow, I'm going to talk about, or tomorrow on Wednesday, I'm going to talk to all the other Algebra 2 teachers to ask, hey, are you going to give students a choice, or are you going to force them to do one and the other? And then by the time you have your review, I'll have a clear-cut answer of what I'm going to expect you guys to do on the test. Okay? All right, cool. Now, can I erase this? Is everyone okay with that? All right, so let's go ahead and find and solve this. Now, this is where what I would say the money is made, because this is where you see the majority of some mistakes. Now, let me rewrite the problem that I asked you guys to do. It was -2g of c squared minus 5 with those brackets, right? Now, the first thing that you need to do when you analyze a problem is understand what they're asking you to do. They're telling you to do -2 times g of whatever c squared is minus 5. So I can clearly see here that I need to evaluate my g function when my input is c squared minus 5. So where's my g function? It is g of whatever x equals is equal to a -3 times whatever x is minus 4. And again, what I like to do is just leave open parentheses everywhere I have an x, so I can go back and input whatever my input is, which is a c squared minus 5. Now, g of c squared minus 5 is what you're looking for. This is what is equal to. Let's start using our PEMDAS. Is there any work I can do inside those parentheses? No, right? Because it's just a c squared minus 5. You can't combine those. Is there any exponents? Technically, but can you simplify c squared any way, shape, or form? No. So let's go to multiplication. Let's distribute that -3. This ends up being -3 squared plus 15 minus that 4. Don't forget the -4. And now you do the addition, subtraction, and clearly we can only combine the last two latter parts, right? 15 minus 4 would be 11. There you go. So g of c squared minus 5 equals -3c squared plus 11. I know it feels like we should be done, but are we really? No, because remember the original problem. What are they telling you to do? They're telling you to take -2 and multiply it to whatever g of c squared minus 5 is. And what is g of c squared minus 5? Hopefully everyone's saying is, what we found. -3c squared plus 11. And then now you just have to simplify. So you can start all over with the process, the whole PEMDAS. Well, you'll notice that since you're only multiplying it by 2, that is really all you have to do. you end up with a positive c squared. So you end up with a positive c squared minus 22. Does that make sense when you distribute it there? Because all you're distributing is that negative 2. And once you distribute that negative 2, you're going to end up with that positive c squared and then the negative 22. Any questions at all? Okay, cool. All right, so let's review on how to find the degree and the leading coefficient. So that way, when I tell you about what that does for our graphs, you know how to start from the very beginning. If I give you a polynomial, you'll know what your graphs look like if you know how to find the degree and the leading coefficient. So let's start with the easiest one, which is a degree. Now, a degree is pretty easy to find because all you literally have to do is look at all the exponents of your variable and look for the biggest one, because whatever the biggest exponent is of all your variables is your degree. So I have a 6 and a 2. A 6 is clearly the bigger number, so that means that this is a 6-degree polynomial. The leading coefficient is the coefficient in front of your biggest degree, so it's going to be a positive 5. Okay? So what do you guys think about this one? What would be the degree of our second polynomial? 5. Absolutely right, because notice that it is the biggest exponent to our variable. What would be our leading coefficient? 3. More specifically, negative 3, okay? Keep in mind that the sign stays the same. Now that's cool and all, but what does that do for us? So what I did here is give you guys 6 graphs of different degree of polynomials. And what we're going to do is really, one, learn how to describe graphs, and then kind of see the how would I say, the patterns within them. So looking at this 6 problems, the first thing I want you to be able to do is be able to describe graphs, okay? Now, does anybody know what it means to describe graphs? It's okay. So whenever I tell you to describe graphs, what I'm really telling you to do is to tell me what the end behaviors of your graphs are. So a lot of times you will see in books and in questions, they'll say, hey, describe the end behavior. Now, whenever you have a graph, you have 2 sides of a graph. You have the left side and the right side. So if I start off with this linear function that has a degree of 1, if I told you, hey, describe the end behavior, describe the behaviors of this graph, what I want you to do is describe what happens to your graph when you go to the left side and what happens to your graph when you go to the right side. Now, of course, you need to be able to mathematically show or explain it, so let's go ahead and do that. Now, again, you're describing the left side of your graph and the right side. When you're going to the left side of the graph, notice in the right and left, what are you looking at? What axis are you looking at? The x, right? When you go left to right, you are talking about the x-axis. Now, if you're going to the left, what is happening to your x's? Are they going to the positive direction or the negative direction? You know what I mean by that? Positive. So let's say that this is x equals 0. And as you're going to the left side of the graph, what is happening to your x's? Are they getting bigger or smaller? Smaller, because you're going to the negative direction. And if you're going to the right from their 0, notice that your x's are getting positive. So the way to describe the behavior of this graph going to the left, aka the negative, is to literally tell the reader, hey, as my x's go, and I'm going to say go with an arrow, to negative infinity. So as I go to the negative values, this is what my graph is doing. So in this specific situation, the way you say graph is you say the function, f of x. Now let's think about this. You are telling me as x goes to negative infinity, so that means as you're going to the left, so notice I'm tracing my graph to the left, what is happening to it? Is going up or down? Down. So that means your function is going to the positive or the negative direction. Negative, so it goes to negative infinity. So that is how you describe your graph going to the left. Now let's describe our graph going to the right. Now it's pretty much the same thing, except now as your x's go where? Are we going to the positive x direction or the negative x direction when I speak of going to the right? Positive. So as x goes to the positive, direction, what is happening to our function? Is it going positive or negative? Going positive, absolutely right. Now what I want you guys to do is to describe the graphs. For all the other graphs, just leave out 0 because I'll explain why we leave out 0 in mostly all occasions when it comes to math. Okay? So try number 2. I'll go over this in like a quick second too, just to kind of make sure that you're going down the right direction. So again, whenever they're telling you to describe end behavior, they're just telling you really to describe the two ends of your graph. Now, whenever you're looking at two ends of your graph, you're going to be looking to the left side and the right side. So you need to be able to mathematically be able to tell the reader, hey, I'm talking about the left or the right. And it's actually quite easy because when you go to the left, that is where your x's get negative. Now let me change colors to make sure that you distinguish them between the other ones. So as your x goes to negative infinity, what is happening to your function? And when you're going to the right, you're going to pretty much say the same thing, except that you're going to be going to the positive direction because that's where your x's are getting positive. That is how you tell the reader, hey, I'm talking about the right side or the left side. And then now you just have to talk about the functions. So as your x's go to negative infinity, aka the right side of the graph, what is happening to your graph as it goes farther and farther left? Is it going up or down? Up. So that means it's going to the positive infinity because remember, up is just the y direction. It's where the positives are at. And of course, down would be the negatives because that's where the down. So degree of 2, what is happening to your function as your x's go to positive infinity? So as you go to the right, what is happening to your graph? It goes up, aka it's going to positive infinity, right? Same thing, really. So try number these 5 or these other 3, and then we will go over those really quickly again and you see if you're getting the describing. Once you get to describing, the other stuff is really simple. So all right, so everybody seems to be doing really well in describing the end behaviors of graphs. Now, if you guys want to go into any type of STEM fields or if you're going to take pre-calculus, this is going to be something that's really important in terms of your beginning of analyzing graphs. So let's make sure you learn it, pretty good. So whenever you're describing end behaviors, there's a left end and a right end. You need to make sure that you are able to tell the reader which one you're referring to. And the way I like to do it, because they always do that, I just always start with, okay, my x is going to negative infinity. That is telling me it's the left. And I also say it's going to positive infinity because that's when I'm talking about the right. And then I go ahead and analyze the graph. So as my x's go to negative infinity, that's the left side. What is happening to my graph? I can clearly see that it keeps going down and down. So that means it's going to go all the way to negative infinity. If I look at the other side, where my x is going to positive infinity, I can see that it's going up. So that means that your f of x is going to positive infinity. And let's go ahead and do the same thing to the 4th degree one. So x is going to go to a negative infinity, and then x is going to go to a positive infinity. As it's going to the left, aka the negative infinity, notice that your graph is going up. That means your f of x is going to positive infinity. Now, as you're going to the right, notice that your f of x is also going up, so that means it's going to go to positive infinity as well. Okay? Last but not least, let's do the 5th degree. X is going to a negative infinity, x is going to a positive infinity, aka left or right. When you go to the left, the negative infinity is going down, so that means your f of x goes to negative infinity. Now, as your x's go to positive infinity, the right side, it's going up, so that means it's going to go to positive infinity. Okay. I know it's really small, I do apologize by that. But let's kind of look at all these examples here. Notice that we have a 1st degree, 2nd degree. Well, first, let me finish the degree of 0. Notice as your x's go to negative infinity, that is your graph going up or down? Neither. So technically, your f of x is going to a constant, whatever the constant is. Now, the reason why I left it out to begin with, because notice it doesn't follow any patterns. And this goes for pretty much all the rules of math when involving 0. If you ever find some patterns and you usually use 0, it never really works. So that's why as math people usually leave it out. So let's finish the other side. As x goes to positive infinity, your f of x will also be going to that constant. Now, before we even go from there, like what I was trying to get at, is I want you guys to look at your guys' degrees and analyze their end behaviors and see if you can see any patterns within degrees. What I'm trying to get at is I want you to think of, if you look at these degrees, this is what the end behavior happens. If you look at these degrees, this is what the end behavior happens. Can you guys notice anything? What is it? No? No one got it? Figured it out? What do you guys notice? Kind of? Joshua, I feel like you got something. Positives go up? Positive. So if you have a positive degree? Yes, sir.
You have an even degree, they both go up and even.
They
go up and down.
There we go. That's what I think. I knew what you were saying, but I didn't want to say it. Now I have no clue why. Yeah, so let's focus on these. First, I like to look at the even degrees. Notice if you look at all the even degrees, what do you notice about them? They're going the same direction. This is the way I like to memorize it. If you're ever given an even degree polynomial, the end behaviors are going to be going in the same direction because they're even. They're going to evenly go the same direction. Now, what if you get odd degrees? So notice I'm going to highlight that with this ugly green. If you're given odd degrees, they're going to be at odds of each other. So they're going to go the same direction or opposite direction. Opposite. And that is something you just got to train your mind to kind of connect. That when you see an even degree polynomial, they're going to go the same direction. And when they have an odd, you're going to have an odd. Or they're going to be at odds and go opposite directions. Now let's make sure that we have this in very clear, concise notes and bring in a little bit of geometry into this. Now, just like we talked about, if we have odd degrees with a positive leading coefficient, we know that they're going to be at odds. So they're going to go opposite directions. And more specifically, they're going to go down and then they're going to end up going up. Now, do you guys remember what happens when you have a negative leading coefficient? If you ever multiply any function by a negative, what happens to your graph? Do you guys remember? They what? They flip. So I know if I have an odd degree with a positive, it's going to go down then up. What's going to happen with the negative? Instead of going from down, it's going to go up. Instead of ending up, you're going to go down. And you'll notice that the same thing happens with even degrees. You know that they're even, so they're going to be in an even race. They're both going to end up going up. That's specifically when you have a positive coefficient. But if you have an even degree with a negative coefficient, what's going to happen with those end behaviors? They're going to go what? They're both going to be going still in the same direction, but this time down. I would say that this is pretty much the number one thing that I would want you to take away. I believe when you do pre-calculus, I think there's a pre-calc teacher that does like a dance, even odd, and it's pretty cool, but obviously I'm not that cool, so that's where that comes from.